Hello friends, now we will discuss another important diode, that is light emitting diode. The light emitting diode basically works on the principle of emission of light from a forward biased PN junction. Let us see the operation of light emitting diode. This is a simple, which is PN junction diode. So this side is P, this side is N. So this is forward biased with a suitable battery, that is forward biasing voltage. This is current limiting resistance. When you forward bias the diode, what will happen? We have already seen there is large number of holes injected from this side, and you will find after injection here reduces exponentially. That is because of diffusion. Similarly, large number of electrons are diffused from this side, and that is like this. Concentration reduces exponentially. This injection of holes from P side to N side is called minority injection, and that is called low level injection. Similarly, on this side, when electrons are injected from N side to P side, this is again minority injection. So you can see in this region, this is the area where concentration of holes is very high, and large recombination will be taking large level of recombination will be taking place in this region of the junction and this region of the junction. So when we have a forward bias diode, the minority carriers are injected across the junction of the diode, and there is a recombination taking place near the depletion layer, near the junction. And when recombination takes place, if you remember the energy band diagram, this is conduction band, this is valence band. So during recombination process, an electron will be jumping from conduction band to valence band directly if the semiconductor of the diode is direct band gap semiconductor. I hope you remember the direct band gap semiconductors. Those are the semiconductors where electron directly jump back from conduction band to valence band. Semiconductors also, that is called indirect band gap semiconductors. In case of indirect band gap semiconductor, the electron comes at certain intermediate energy level from the conduction band, and then it is maybe sometimes it is excited back to this, but it does not come directly but come to some intermediate energy level. So this is called indirect band gap semiconductor. So when you have a PN junction diode which is made of the semiconductor that is direct band gap semiconductor, so what will happen? This electron, while jumping from here to here, will radiate its energy in the form of radiation, and that is nothing but light, visible light. That may be not is, that may be visible light, because this energy lost by the electron when it jumps back from conduction band to valence band is equal to the energy of the radiation emitted by the electron while jumping from conduction band to valence band. I hope you remember the concept. Where H, remember, whenever electron and hole recombine, or in other words, whenever electron jumps from conduction band to valence band, it loses the energy equal to the band gap. That energy is always in the form of radiation, and the energy carried by the radiation must be equal to the band gap. So the energy carried by the radiation is given by h nu, where h is Planck's constant, nu is frequency of the radiation, and Eg is the band gap. And we know the frequency of the radiation is nothing but c by lambda, where c is velocity of radiation or velocity of light, and lambda is wavelength. So this gives the band gap is equal to Hc by lambda. Fine. We know H is Planck's constant, that is approximately equal to 6.23 into 10 power minus 34 joules per second. C is 3 into 10 raised to power 8 meter per second for radiation. So when you multiply these two, I will not be going into that calculation and all. I will be writing directly the band gap is equal to 1.24 by lambda into 10 raised to power minus 6. Fine. And this gives the wavelength of the light emitted from the junction area of the diode is these many meters, that is band gap. But remember, energy Eg must be, that is band gap in electron volt. If it is in electron volt, this will be in meter. I will rewrite it further. The wavelength lambda is equal to 1.24 by the band gap, that many micrometer. This expression is very important. There are plenty of questions on this formula, that is on LED, that is on this light emitting diode, or in semiconductors as well. You can rewrite, but remember here band gap is always in electron volt, that is you must take the band gap in electron volt. That is what you need to remember. And what is 1 electron volt? 1 electron volt is 1.6 into 10 raised to power minus 19 what joules. That is the definition of electron volt. So 1 electron volt is equal to this. So I can rewrite this equation further. Lambda is equal to 12400. I can rewrite in terms of angstrom, that is angstrom, where 1 angstrom is equal to 10 raised to power minus 10 meter. That is your another relationship. Fine. So you may be given question. Let us see few materials where you may be having the question. Say the most commonly used material. Let us talk about most commonly used material. If there is a material which emits the radiation in visible spectrum of electromagnetic spectrum, then you will be able to see the light coming out of the junction area of the diode, and that is your light emitting diode. So light emitting diode works on the principle of emission of light from the junction of a forward biased diode. Fine. Say for example, we know gallium arsenide has what? The band gap of how much? 1.4 electron volt. That is the standard value of the band gap in case of gallium arsenide. Similarly, for silicon, band gap is how much? 1.1 electron volt. Similarly, for germanium, its band gap is 0.71 electron volt approximately. I am just giving the approximate value. Fine. So for germanium, what will be the lambda? Lambda is equal to 1.24 by 1.4, that many micrometers. But remember, gallium arsenide is most commonly used material for fabrication of LED. This is the most commonly used material, and there are a lot of questions in engineering services on this point itself. Question will be like this: which of the following material is used for fabrication of LED? And you will find one option, that is gallium arsenide. Fine. And what are the other materials? The other materials are what? Other materials used for LED. Those are nothing but gallium phosphide, you have indium that is antimony. Then you have indium phosphide. So there are plenty of materials which are used, and gallium arsenide is used for green light emission. But there is interesting point here, another important point to be noted here. Silicon is not used, not even germanium, but silicon, when you talk about fabrication, silicon is not used for LED. Why? Because it is indirect conductor. This is important point again. There are a lot of questions in engineering services. Silicon is not used for fabrication of LED. That is because it is indirect band gap semiconductor. So you won't be getting that radiation. It won't be efficient for that purpose. Fine. Sometimes question is, which of the following material is indirect band gap, and the silicon will be one of the option. Fine. So this is your light emitting diode. So some points to be remembered are, what are the points? LED works in forward bias mode. LED emits light from the junction area. The emission of light is basically recombination of the carriers near the junction area, recombination of injected minority carriers near the junction area. That is the basic principle of working of light emitting diode. This is a small topic. This is only the part you need to remember, and there are questions in GATE and engineering services from light emitting diode. I hope you will remember all the points whatever we have discussed. So this is all about LED. So I will be discussing one more diode, that is Schottky diode. That is not important for GATE but for engineering services. Till then, just wait for my next video, and I will be discussing the questions from LED which have appeared in GATE, but that will be discussed separately in another video. Thank you for watching.